Good morning, student. This lecture related to queuing models, of which classification of queuing models, especially for Poisson queues. Actually, it is the fundamental classification in queuing system, because there is a Poisson queues, non-Poisson queues, general service orders, etc. so on. But it is the fundamental. As per our syllabus, it is the fundamental model, that is Poisson Q MM1. Before going to the classification, just we recall the lecture 1 and 2 related to stochastic process and outline of queuing theory. The second one is pure birth process or the distribution of arrivals and service times distribution. Of course, we know that the distributions of arrivals is Poisson, the service times distribution is exponential. Now, in this model, first of all, we go to MM1 infinity FIFO queuing model. What it could be? In the first lecture, any queuing system can be notated for the suggestion of Kendall is A, B, C, D and E. A representing the arrival process, B representing the service time process and C representing the number of service channels, and D representing the capacity of the system. Finally, E representing queue discipline. So, in this model, M representing the Poisson arrivals, the second M representing the service times are exponential. This one representing the number of service channels in a service station, only one service channel. Now, this infinity stands for the capacity of the system is infinite. This FIFO stands for queue discipline, first in, first out. Okay, right. Now, a single channel facility or one queue, one service station facility. This means that there is only one queue in which the customer waits till the service points is ready to take him for servicing. Like a library example that is already discussed in lecture 1 in queuing theory. Okay. Now, what about the representation of MM1 queuing model? Just I said M denotes Poisson arrivals or exponential inter-arrival times, also accepted. Second M denotes Poisson departures or exponential service times. Okay. One denotes single service station. Okay. And capacity of the system is infinite. FS stands for first in, first out. Okay. This is called a queue discipline. So, arrival entered into the system is waiting in queue for getting the service from the service center. After the service, he exit from the system. That is a pattern. Now, as for the second lecture, we know that the arrival process of any customer is always a Poisson. That is P and T is equal to e power minus lambda t into lambda t whole power n by n factorial, where n is equal to 0, 1, etc. so on, that already derived in the lecture 2. Similarly, the inter-arrival times or service time distribution follows an exponential distribution that is also derived as f of x is equal to mu into e power minus mu t, where mu is the arrival rate, mu is the service times service rate or inter-arrival rate. Its mean is 1 by mu, variance is 1 by mu square. That is also derived in the lecture 2. Now, our interest in this lecture is the steady state solution of the model. What is the steady state solution? How it is defined? The operating characteristics of any queuing system is a function of a time transient state solution. Is independent of time steady state solution. So in our syllabus structure we derived the steady state solutions of queuing model MM1 with infinite capacity. Understood my point? Okay. Now let us consider a counting process n of t where t greater than 0. Counting process is always integer valued process. Student, my interest is the state of the system is fixed. The state of the system is fixed. What is the state we are fixing here? N. Why? Because we defined PNT. What is the PNT? Probability that the counting process expecting n customers or assuming n customers in the length of the time interval 0 to t. 0 to t. Okay. Now in this MM1 model, the state is fixed as in the previous at n. So state of the system is existed at n. There is no way to change. So what are the possibilities arrival? What are the possibilities are getting the system should be fixed? Okay. The first one, suppose the state is at n, we won't allow any customer, means no arrival, no service done at system. The state remains n. Or suppose there is state is n, one arrival entered in the system, immediately we made service to the same arrival, the state remains constant. State remains constant. Or suppose the state at n minus 1 possible. What we have to do that? Let them to make into n. So we entered into one arrival, we invited to one arrival, no service can done. No service can done. Right? Suppose the state at n plus 1, the state at n plus 1, what we have to make? The system, the state become make it state is at n, no arrival will be invited, but one customer serviced immediately send out. Then the state becomes n. Suppose n plus 2 make service to 2 customers. Suppose n minus 2, we invited to 2 customers as arrival. Okay. So this process is continued up to all the events. Up to all the events. Right. So how many events are possible right now? The possible events are A1, A2, A3, A4, etc. up to A7. But our interest is only up to A4. Why? The reason is very clear. More than 2 units in the length of the time interval h is always negligible, which is a small order function. So either arrival or service at any of the stage, okay, greater than 1 is always negligible. Is always negligible. So the first column representing arrivals, the second the third column representing services. Now the second column, this column representing the state of the system we mentioned here. So the possible events are A1, A2, A3, A4, A5, A6 and A7. Okay. But our interest very clear about up to 4 events A1, A2, A3 and A4. Other than that the negligible about its probability. Are you okay na? Right. Now we can write that is equal to Pn T plus H. What is the Pn T plus H here? Probability that the counting process assumed n customers. It is possible the state of the system at n, no arrival, no service. Just we mentioned in the above table. right? Or second one, what is the second one here? If the state of the system at n, one arrival entered into the H, the same arrival immediately makes service. Again the state at n, it remains constant. Suppose n minus 1, our interest is n, the state is n. So n minus 1 is possible, immediately we invited to a new customer but not do any service. Suppose the state at n plus 1, no arrival is invited but immediately make one service, right? Similarly, suppose n plus 2, no arrival is invited but immediately we made service to 2 customers. Its probability is always negligible, right? Similarly, n minus 2, our interest is always n, state is n. So 2 arrivals in H, length of the time interval H, but no service. So this probability is negligible because more than 1, the respective probability in the time interval H is always a small order function. So n minus j state of the system possible, j arrivals, no service. Suppose n plus j is the system, state of the system, no arrivals, j services. So j is greater than or equal to 2. Greater than or equal to 2. So that whenever greater than or equal to 2, that probability is always negligible. Those are acting as a mutually exclusive events, which is also similar to the lecture 2. Now we adapt to the probability. What update? So the state of the system is P and T. No arrival, no service. No arrival means axiom 3, P of H is equal to 1 minus lambda H plus small order h, that is already discussed in the previous chapter, previous lecture, right? Similarly, no arrival, no service. Suppose the state is at n, 1 arrival and 1 service. 1 arrival probability is a lambda h plus small order h. 1 service is mu h plus small order h. What is the mu here? Service rate. What is the lambda here? Arrival rate. Suppose the state is at n minus 1. Let them to make it to n. So what we have to do that immediately? 1 arrival is immediately invited but not any service. No service. Suppose the state at n plus 1. Let them to make it to n. What we have to do that here? No arrival is invited but immediately we made service to one customer. Right? Similarly, if more than 1 means greater than or equal to 2, okay, no arrival is entered, we made immediately service to the customers. Okay, similarly n minus j state, what we have to do that? We entered into j customers immediately, invited into j customers, no service we can make. Of course, these 4 terms, the last these 2 terms completely small order h, because more than 1 is always negligible about its probability. Okay, right. Now that will be simplified as, what is the first one here? The first one simplified as, this is equal to, just come to the point here, we multiplied with an algebraic multiplication, 1 minus lambda h. Okay, now small order h into 1, again the small order h. Now we multiplied mu h into 1, so minus mu h. Now we multiplied with lambda h into mu h, that is lambda h into mu h. This is also negligible. Why? Because h is a very small interval, so that lambda mu into h, that is negligible quantity. Okay, this is the small order h. Coming with the second one. Okay, the same algebraic multiplication, lambda h into mu h plus small order h. Right? Again, this is also simplified with Pn minus 1 multiplied lambda h, okay, minus lambda h into mu h plus small order h. Right? Now again this n plus 1 state we multiplied, what is it? Minus mu h, right? And again minus lambda h into mu h plus small order h. More than 1 means greater than or equal to 2, always small order h. Again we simplified the term, the above term we simplified. What we get here? That is equal to here 1 minus lambda p and t into 1 minus lambda h minus mu h. This term becomes negligible because h is very less, the length of the interval is very small. H into h becomes h square, that is again small. It is a very small, it is a negligible interval, right? The very small, so that the multiplication of two intervals, so small intervals again small, it is always less than. Suppose the length of the interval h is less than one quantity, multiply with the two less than one quantities, again also less than 1. Okay, so we negligible it, right? Again plus small order h. Why? Because you may ask one question, there is, sir, you talk about it is simply negligible. The reason is very clear. I am not much more interested about transient state solution. What I am interested here? Steady state solution. Steady state solution, what it becomes here? Independent of time. What is the h here? The time and length of the time interval. Because of that reason, that quantity is negligible, right? Again, coming to the p and t, here lambda into mu into h square, it is also negligible, so that term is not coming into the next step. Now here we multiplied p n minus 1 lambda h plus small order h, because this quantity is negligible. Now n plus 1, this quantity is negligible, so that mu h plus small order h plus etc. That all the terms more than 1 greater than or equal to the term is called small order h plus small order h, right? Again simplified the same term, you will get as, what is it? P n t minus lambda h, means we multiplied with separately with p n t. Here we multiply with p n t minus lambda h into p n t minus mu h into p n t, looking like that. Again we simplified, okay, the term. What we get here? Once we separately multiplied with p n t minus lambda h p n t minus mu h p n t plus small order h. Similarly we multiplied this state n minus 1, okay, and n plus 1, right? Now just come to the point here, what it could be here. Those algebraic multiplications and addition and subtraction, all the equations we can join as p n t minus lambda h small order p n t minus mu h into p n t plus lambda h into, just I will show that here, right? So p n t minus lambda h into p n t, right, minus mu h into p n t, right, plus lambda h into pn minus 1t, again mu h into pn plus 1t, sum of all these small order functions becomes small order, right? Now here minus lambda minus mu, pnt is the common, okay, we are taking the pnt in the common, right? Now the next step, what is the next step here? See that here h, here also h, here also h, so the entire equation divided with x. Okay, here this p and t take in the left hand side, right? So dividing the h. Okay, now we consider limit h tends to 0. This term becomes as p n dash t. P n dash t. Okay, minus lambda plus mu into p n t plus lambda into p n minus 1t plus mu into p n minus p n plus 1t. Just dear student, you observed there is a n minus 1 state na, so we need one arrival. What is the arrival rate here? Lambda. Here n plus 1 state na, so what we have to do that? We make service to some customer. What is the service rate here? Mu. Here state is, what is the state here? N. So one arrival, no arrival, and sorry, one arrival, one service. Just you observe the term without any confusion. Okay, this is valid when n greater than 0. Suppose n is equal to 0. Come to the point here. The state of the system, I would like to make it 0. So no arrival. Suppose there is no arrival, is there any question for service? No. So there is no service. State is already 0. No arrival in the system. So what about the service? There is no question of service. Okay, second one. Suppose the state is at 0, possibility for one arrival entered in the system, we made service to the same customer, left it. Suppose the state of the system at 1, no arrival is invited, we made service to one customer. So there are three possibilities. These three possibilities are A1, A2, A3. They are mutually exclusive. Again, similar lines we can write as the state of the system at 0, no arrival. State of the system is 0, one arrival, one service. State of the system at 1, no arrival and one service. Okay, again we simplified in the similar lines, multiplied with everything. Okay, and we make it finally you get P0 T plus H. What is the meaning of P0 T plus H here? P0 T plus H, that is equal to, there are no customer in the length of the time interval T plus H is equal to P0 T minus lambda H into P0 T plus mu H into P1 T plus small order H. See, this P0 T taken the left hand side. Okay, right. Now the entire equation divided with H. H. What it becomes here? Once we divided the H here H cancel. The left hand side term is nothing but P0 T plus H minus P0 T by H. Right. Now we consider limit to both side. Okay. Now this function, small order function, becomes 0. These two are independent of H, so that the equation becomes as, what is the equation here? That equation is equal to, what is the equation here? The equation is equal to P dash 0 T is equal to minus lambda P0 T plus mu into P1 T. See that equation 2. Now equation 1 and 2 we can written as the difference equations. What is it? N greater than or equal to, this is already mentioned in equation 1. N is equal to 0 we mentioned into equation 2. So equation 1 representing more than 0 customers or greater than or equal to 1 customer, the state of the system. So P dash NT is equal to minus lambda plus mu PNT plus lambda into Pn minus 1 into T plus mu into Pn minus 1 into T. Just we mentioned here, there is the state at n minus 1, we expected one arrival. The state is n plus 1, we made service to one customer, because our interest is the state should be at n. Okay, right. Now n is equal to 0. What we get here? N is equal to 0 minus P dash 0 T is equal to minus lambda P0 T plus mu into P1 T. These equation 1 and 2 are called difference equations. Yes. In your hand, difference equations. Those are solved by using separation of the variables. That is already done into the previous model, distribution of arrivals. In that time, I am not interested about steady state solution. But this lecture, our interest is the steady state solution of MM1 model. The steady state solution, when we call a solution is a steady state solution, that is, the operating characteristics of a queuing model are independent of time. Okay, so a queuing system is said to be steady state if its operating characteristics are independent of time. What about the transient state solution? The queuing system is said to be transient state solution if its operating characteristics are depend upon time. Okay, so in our model we need to find the steady state solution. the steady state solution. Are you okay na? Right. How do you get it? In a steady state solution, as t tends to infinity, d by dt of p and t is equal to 0. So this term is nothing but d by dt of p0t. p0t. Now this term representing d by dt of p and t. d by dt of p and t. As per the rule of steady state solution, this term becomes 0. The left hand side terms becomes 0. So we write, what we write here? The left hand side terms are 0 for n greater than or equal to 1. What is it? Minus lambda plus mu into pn plus lambda into pn minus 1 plus mu into pn minus 1. So just we omitted a time. See that the term is here like the t, that the time is independent of the time, so that this we can written as only minus of lambda plus mu pn plus lambda into pn minus 1 plus mu into pn plus 1, similar to the second equation also. Now from equation 2, what we are writing here? 0 is equal to minus lambda p naught plus mu p1. Right? Now this this negative quantity take on the right hand side. Okay. Now you can write mu p1 is equal to lambda into p naught. Right? Now p1 is equal to lambda by mu into p naught. What is the lambda by mu? This is already discussed in the chapter, in the lecture 1. Lambda by mu is nothing but the ratio between the arrival rate and service rate is traffic intensity, that is denoted by rho. So what is the traffic intensity here? The ratio between arrival rate and service rate. So P1 is equal to rho into P naught. Okay na? Right. Now from equation 1, that is, say that equation 3. Now equation 1, what is the equation 1 here? Minus of lambda plus mu pn plus lambda into pn minus 1 plus mu into n plus 1. Put n is equal to 1 in that equation. What it becomes here? Minus of lambda plus mu p1 plus lambda into p 1 minus 1, n is equal to 1 here, right? Mu into p 1 plus 1. 1 plus 1. Again we write that is equal to here. This is 0 is equal to minus of lambda plus mu p1 lambda p naught plus mu into p2. Again by simplification, what we get here? Mu into p2 is equal to lambda plus mu p1 minus lambda p naught. Now again simplified as just instead of p1, what we write here? From equation 3, lambda by mu into p naught. Just we observed here. What is the p naught here? P1 here? P1 is equal to lambda by mu into p naught. That term is equivalent to p1. So we can write instead of p1, what we written as lambda by mu into p naught minus lambda p naught. Okay, right. Now this term is, what is it? Simplify that. Lambda plus mu into lambda by mu. Here p naught is common. Okay, shall we consider the p naught? Alright. Now by taking the LCM, mu is the denominator, lambda square, just you multiply it, lambda square plus lambda mu, here minus lambda mu. Both the terms are cancelled. What remains here? Lambda square by mu into p naught. Okay na? Right. Now this mu taken the right hand side, what we get here? Lambda square by mu square into p naught. right? Now the same term we may written as P2 is equal to lambda by mu whole square by P naught, right? That is equal to what is the lambda by mu? Rho square by P naught, rho square into P naught. Okay, that is P2, right? By using the same iterative method, n is equal to 2. N is equal to 2. So n is equal to 2, what we get here? 0 is equal to, from equation 2. What is the equation 2 here? Sorry, equation 1. Minus of lambda plus mu P2 plus lambda into 2 minus 1 n minus 1 plus mu into n plus 1. Mu into n plus 1. That is equal to minus of lambda plus mu P2 plus lambda into P1 plus mu into P3. Mu into P3. Okay. Again we simplified as here lambda plus mu into P2. Okay. Here lambda P1 plus mu into P3. This mu into P3 taken the left hand side quantity. Right. So minus lambda P1. Minus lambda P1. Now you the people to know that what is the P2? P2 is equal to lambda by mu whole square by P naught minus P1 is equal to lambda by mu into P naught. Lambda by mu into P naught. Okay, right. Now again we simplified the term. Once we simplify the term, what we get here? Just here. So mu lambda square by mu square. Mu square is the LCM, right? Now we multiply with lambda cube plus lambda square mu minus here lambda square mu, because mu here just we multiplied with what is that? The P not taking the common. What remain here? Lambda plus mu into lambda square by mu square minus here lambda square by mu. Suppose we consider the LCM. What is the LCM here? Mu square. LCM is the mu square. So lambda cube plus lambda square mu plus minus lambda square mu. So lambda square mu both are, one is the positive, another one is the negative, both are cancelled. So what is remaining here? The remaining term is lambda cube by mu square into P naught. Right? Now that is equal to again what it could be? P3. What is the P3 here? Lambda cube by mu cube, okay, into P naught. Okay, now that term again we may write lambda by mu whole cube by P naught. What is the lambda by mu? That is a traffic intensity, the ratio between the arrival rate as well as service rate. Okay, so this is rho cube by P naught. So P3 is equal to rho cube by P naught. Similarly for n stands for there are n customers in the system, the state of the system at n in the time interval 0 to t plus h. But strictly speaks, in a steady state solution, the time is totally independent of given function. Okay, so the Pn is equal to what I am writing Pn here. See that P3 rho cube. So Pn is equal to lambda by mu whole power n by P naught. That is equal to rho power n by P naught. What is the P naught? The question. P naught is at the initial stage, the probability that no customer at the initial time epoch. How do you find it? We know that Pn. What is the Pn here? The probability that the counting process assumed n customers. Am I right? So this Pn is nothing but a probability function. If it is a probability function, it should have the properties of non-negativity, normality. Non-negativity and normality. So what is the non-negativity? P of x is greater than or equal to 0. What about the normality? Sum of the probability is equal to 1. Sum of the probability is equal to 1. Now you know that in a chapter 1 random variables and probability distributions, we want to find the constant whenever a probability distribution, discrete probability distribution provided. 0 x random variable takes the value 0 1 2 etc so on, okay, up to 10. Now the probability is k, 2k, 3k, k square, k plus 1, okay, etc so on. How do you find the constant? The sum of the property of normality is our interest. Okay, so by using the property of normality, we can write n is equal to 0 to infinity, Pn is equal to 1. Instead of Pn, what I am writing here, the instead of Pn we can written as rho power n into P naught is equal to 1. Here this summation running on n, so P naught remains constant, taking outside. Okay, now expanding the summation. Once we expanding the summation, what we get here, P naught into 1 plus rho power 1, okay, plus rho square plus rho cube etc so on, that is equal to 1. What it could be here? This is sum of infinite GP with common ratio is equal to rho. What is the sum here? 1 by 1 minus rho. So P naught into 1 by 1 minus rho is equal to 1, which implies P naught is equal to 1 minus rho. That is equal to 1 minus, what is the rho here? Lambda by mu. Lambda by mu. Okay, now once we know that the initial probability P naught, then the steady state solution of the MM1 model, what is that? That is equal to Pn is equal to lambda by mu whole power n into P naught, or rho power n into P naught, or rho power n into 1 minus rho. Why? Because 1 minus rho, P naught is equal to 1 minus rho is equal to lambda by mu whole power n into 1 minus lambda by mu. 1 minus lambda by mu. Whatever it is the same. Because sometimes in applications they are using this formula, sometimes they are using this formula, like that. So you can remember the steady state solution of the model MM1 is equal to, what is it? Lambda by mu whole power n into P naught, or rho power n into 1 minus rho. What is the meaning of MM1? M representing the arrival process. What is the arrival process here? Poisson. The second M representing service process, service mechanism, or service times distribution. What is the service times distribution here? That representing an exponential. That is also denoted by M. 1 representing, what is the M here? The capacity of the system. The capacity of the system. Now infinity, what is the infinity here? Infinity stands for the capacity of the system is infinite. Okay, and FIFO, what is the FIFO here? Q discipline, first come first serve, or first in first out, that is called Q discipline. What is the Q discipline here? A rule formation of the queue, or a rule selecting a customer when they are waiting in a waiting line for doing service. So that we derived the steady state solutions for any model, not only for this MM1 or MMC or Poisson or non-Poisson Qs. We should have to derive it for n is equal to 0 and n is equal to 1. See that in our model also we derived, what we derived here? N is equal to 0. First of all, this is equal to n is equal to 0. Okay, and the second one is n is equal to 1. N is equal to 1 means, sorry, n is equal to, the second one, what is it? N is greater than to 0. N is greater than to 0. Set initial stage and n greater than 0. N is equal to 0 means no customer at that time. N is greater than 0 means there will be some integer valued counting process. There is some positive integer valued counting process, right? So you remember In a queuing model MM1, the steady state solution stands for, what is the steady state solution? That is equal to Pn is equal to rho power n into 1 minus rho, or lambda by mu whole power n into 1 minus lambda by mu, 1 minus lambda by mu, where lambda is the arrival rate, mu is the service rate. Okay na? So this is a steady state solution. Okay, now the next class we expected to deliver a lecture on the operating characteristics of the model, MM1 model. So what is the queue length? Okay, what is the waiting time distribution of a customer, right? How much time is waiting in the system, how much time is waiting in the queue, the length of the queuing system, the length of the queue, right? And the ideal time of the queue, the busy period of the queue. These characteristics of a queuing model will be discussed in the next class, right? Thank you very much. You have any doubts, please invited. Before closing this session, you remember MM1 representing the Poisson arrivals, service times distribution is exponential, the number of service channels are 1, the number of service channels are here 1, and the capacity of the system is infinite. The queue discipline adapted here is first in first out. Okay, right. Thank you very much.